Okay, so today we're going to be doing exam review 4, part 2. So all of this is basically going to be about carbohydrates and amino acids, and this is actually like a large part of your exam. So I just wanted to make a little review on this part because this is, I think, like about 40 points of your exam. So it's a good thing to get down already. Okay, so for the first one, we're going to do draw alpha and beta anomers of D-glucose. Sadly, I already told you what kind of glucose it is, like L or D. Told you it's D. But let me just show you the reason that it is D. Okay, so this is D glucose because the periultimate, which just means second to last, I'm sorry, penultimate. Penultimate carbon, which just means second to last, it exhibits the R conformation configuration. There we go. And so just a reminder on how to do RNS, because this one it might be a little bit more difficult just because of that little the carbons that look the same. So I'm gonna zoom into my penultimate carbon, this one right here. And so this is my stereogenic center. And we want to see if this is an S or an R configuration. So we're going to start assigning priorities. So priorities, we assign them by like which one has the most mass. So then what's surrounding is 4 different groups. So a hydrogen, a carbon over here, an oxygen, and a carbon. So 2 of the same groups, right? But they have like more to it. So that's what we're going to try to figure out together. So number 1 priority is going to be oxygen, because out of carbon and oxygen has the most molar mass. Then I move on to my carbons. And this one can be confusing at first, but all you have to do is keep moving on. So I'm going to draw the things that are next to each other. I'm going to draw it with the carbon structures, right? Because just so it doesn't like confuse me. This is like a zoomed in version of my penultimate carbon. And so this is the penultimate carbon, what I'm assigning stereogenic centers for, and we said this one is 1. And so I'm going to look at the next carbon. Since they're the same atom, we're going to move to the next ones after that. So I see that on this carbon on the top, I am connected to an oxygen. And so I look at the carbon on the bottom, it's also connected to an oxygen. Then I'm going to move on from that oxygen. So what else is this carbon connected to? It's also connected to another carbon. Whereas this carbon at the bottom is connected to 2 hydrogens. So you keep moving on, like keep going from stereogenic center to your carbons. And then these carbons are connected to different things. Whichever carbon has the most molar mass, more like side chains and anything, it's going to be your more top priority. Your top priority. So then we assigned 1 right here. This one will be 2. This one will be 3, and this one would be 4. Okay, so then I do my little arrow. So I'm connecting the dots. 1, 2, forget about 4, and then go to 3. So act like 4 is not even there. And so we're going anti-clockwise. So at first you think it's S configuration, right? But then you remember that in Fisher projections, everything that's going, all these horizontal lines, those connections are all on the wedge. So then your least priority, look at how it's on the wedge, your hydrogen is on the wedge. So then that S configuration flips to R. Okay, so we figure out the configuration, and now we need to remember, this is just memorization, that R, we can tell what glucose it is by the configuration, and so R gives you D, a D glucose. If we had an L configuration, it would have given us the L glucose. I mean, S configuration, it would have been L glucose. Oh my god, it's so hot in this room. Okay, cool. The next thing to do the anomers, I need to draw my Haworth projections. So these are kind of easy to draw. I'm just going to do two baseline ones, basic ones. Okay, cool. And so we know that the penultimate carbon exhibits the R configuration, so it's a D-glucose, which means that the terminal carbon, the one that I just circled, is going to go up. So another thing that you have to remember is that D is up and L is down. And that tells you where the terminal carbon, whether the terminal carbon is going to go up or down in the Haworth projection. So since we're D, we're going to go up. How I remember that is like, I used to play basketball, and so they would also always chant like D up. And then for L, I always think like loser down. So then D up, terminal carbon goes up, H2O each, and that's good. So I'm going to say that this is my alpha anomer, my beta anomer, and we're going to go from there. Now I'm gonna name and number and put all my substituents on my Haworth projection, not the alpha carbon right now. And so how you would go about putting these substituents on your Haworth projection is you need to know, whether you go up or down. So how we figure this out is we do a 90-degree flip. So it's going like straight up and then it goes horizontally. And so let me draw it horizontally, like if it's laying down, carbon. 1, 2, 3, 4. Okay, so these are these I guess vertical lines now. They represent all of these substituents. And so when I flip it 90 degrees, look at the camera so you can like figure it out. So this is the little backbone right here, right? This is this right here. And so my OH on this first, on carbon number 2, this is how you number it. My OH on carbon number 2 is going to the right. So if I'm flipping it horizontally, it stays down. Okay, cool. Now let's move on to number 3. So in number 3, your thing is vertical, your spine is vertical, and you have OH on your left. So you flip it 90 degrees and it stays up. So this goes up. Carbon 4 is on the right, flip it 90 degrees and it goes down. The 5th carbon, the OH is on the right side, flip it 90 degrees, it goes down. And there. That'll tell us whether we put it up or down in the Haworth substituents. So now I'm going to number everything. And so the way that I numbered this glucose over here is the way that you usually are going to number your Fisher projections for all of your carbohydrates. And so to show like how I cyclized, how I went from this like stick structure, the skeletal structure kind of, into a cyclized form of this, it's basically like the acetyl and the hemiacetyl reaction. So let me just sidetrack right here. It's like if we're going from a ketone and we're attacking with an alcohol. And so remember that all this does is this is your nucleophile, it attacks. And at the end, if I'm only using one alcohol reagent, one equivalent, then I'm going to get a hemiacetal. And then if I do 2 equivalents, it'll be a full-on acetal, which looks like this. So the only difference between this one is I have an alcohol group and an ether group. So that's a hemiacetal. Whereas in the full-on acetal, I have 2 ether groups. On these that I'm about to do, check it out. So 2, 3, 4, 5, 6. I'm going to do what I usually like to do. We know that we like to make 5 and 6 membered rings. And so for the reaction that I just showed you to make the hemiacetal or the acetal, we went from an oxygen, an OH group being your nucleophile, and we attacked the electrophilic carbonyl carbon. So that's exactly what's going to happen here. So I numbered oxygen as number 6 because usually when I'm doing like any other reaction in OChem 2, I number so that only the atoms that are reacting in my reaction are the ones that are going to be like numbered in my ring. So because I numbered it in this way, it's going to be easier for me to place my substituents how they should be placed. So check it out. 6 is going to be part of my ring, so I'll put it right here. It's connected to 1, and from there I just number everything else. There we go. So that's just how, like, an example of how we cyclize things. 6, 5, 4, 3, 2, 1. Okay, cool. So now that we did that, we're able to place our substituents. So on carbon number 2, my OH group is down, so I'm gonna put it directly down. This is not like a chair conformation where we have like the equatorial and the axial, where it's like slightly up, like to a little, I don't know, it's like not directly up, not directly down. So it's not this situation where we use equatorial and axial. Here you go straight up or straight down. And so for my 3rd carbon, I'm going straight up. For my 4th carbon, straight down. And for my 5th carbon, this is the one that was being attacked, so it's part of the ring. It's this one right here. And then we just have this substituent, but what tells you whether this one is up or down is whether it's D or L sugar. So that one doesn't change. And now we have to worry about the last substituent, which is on my anomeric carbon. So let me just put this right here and put anomeric carbon. And so alpha, that's another thing that you have to remember. So alpha means trans, and beta means cis. So trans, an opposite side, cis, the same side. So this, what we have to like compare it to is a terminal carbon. So if I say I want the alpha anomer, I want it to be trans to the terminal carbon. So then my OH group should go down, because if this is going down, this is going up, it's trans. Okay, cool. Move this. Okay, so I'm gonna put the substituents the same. So OH goes down, OH up, OH down, and your terminal carbon, since it's a D-glucose, it should always go up. CH2OH. And now this time it's a beta anomer, so at the anomeric carbon is where we're going to do the little change. So beta means cis, so my OH group is going to go up. Because if this is up and my terminal carbon is up, they're both cis to each other. Yeah. Okay. And I only put glucose there because this is a molecule you're supposed to like remember. It's how people remember like to draw when they give you like the nomenclature and everything. So how people remember it is the middle finger. So notice how the middle finger only on the left side, the OH will be here. So it kind of looks like this right here. This OH is on the right, on the left, while everything else is on the right and everything. Cool. Sorry. Okay. Now I'm going to do my chair conformation. There you go. They'll have it pre-drawn for you, by the way. So it's telling me my beta anomer, and I'm going to number everything so I don't get confused. So this will be 6, 5, 4, 3, 2, 1. 1 is my anomeric carbon, and it's asking it for it to be beta anomer. Okay, that makes sense. So I'm just gonna do those first. So the carbon that I labeled number 5 is where my terminal carbon should go. It's D, so it goes up. So this is going to be in the equatorial position. Okay. And so it's beta, so it's cis. So at the anomeric carbon, oops, I wrote this wrong. At the anomeric carbon, I should also go up so that they're both going up and they are cis to each other. And then everything else as usual, how we did it right here. So my second carbon is going down, equatorial. Third carbon is going up, equatorial. And the fourth carbon is going down, equatorial. Yeah. And that's how you remember it in biochem too. So whenever you draw the beta anomer, it's going to be all the substituents are going to be in the equatorial position, and that'll change for like the different carbohydrates. So that's how you remember D-glucose. But yeah, this one. Okay, so they're giving you lysine. Draw the predominant species of an amino acid at a pH of 7. So then for these, we know that all the pKa's lower than desired pH, so in this case 7, would be prohibited. So I'm just going to check this pK is lower than 7, and that's all. So only this hydrogen is going to be deprotonated. So I'm going to get all my carbons correct. Deprotonate that oxygen. Everything stays as normal. Everything else stays as normal. Cool. And that should be the predominant species at a pH of 7. And so for isoelectric point, what you do is you grab your most similar functional groups on this compound. So my most similar functional groups are the amine parts. And you add those together and divide by 2. So that's all I'm going to do here. 10.53 plus 8.95 divided by 2. And I have this pre-calculated. And it's 9.74. Okay, so I calculated isoelectric point, but what isoelectric point is the point at which I have a Zwitter ion of this compound right here. And so what Zwitter ion means is it's when your compound is neutral, and that doesn't mean that there's no charge on any of your little functional groups. It just means that these charges may cancel out and stuff. And so let's just check to make sure that we're right, that at this pH we'll get a Zwitter ion. So again, we follow the same rules over here. Any pK below the desired pH, in this case 9.74, will be deprotonated. So let me just draw it out for you. This is just for like the understanding part. This will be deprotonated and this will be deprotonated. So I get NH2, since this is deprotonated, I get a negative charge where my carboxylic acid was, and this amine stays the same. And so notice how here we have a neutral compound because this negative charge and this positive charge cancel out, and we no longer have a charge here. So this is our Zwitter ion. And so that means at this pH, we're pretty correct here because at this pH, we have a neutral compound. Okay. Identify the following as a reducing or non-reducing sugar. And then what makes a reducing sugar a reducing sugar? So what I put for this one was, I don't know, it's going to sound like duh, but I put sugar capable of acting as a reducing agent. Simple sugar containing a hemi functional group on the anomeric carbon. Okay, so it's all dependent on the anomeric carbon and if this anomeric carbon is a hemiacetal, right? So then for each of these, I'm going to look at my anomeric carbon. So for this one, as normal, how we usually looked at it, I numbered the oxygen as a 6 and the anomeric carbon as 1. So this one's the one that we're focused on. We know that hemiacetals have an alcohol group and an ether group. And so for this carbon right here, I have an ether group right here. And this is an ether group, but it's taking away that alcohol that there would have been in order for this to be a hemiacetal. So this right here is not a hemiacetal, therefore is not reducing sugar. Okay, we're doing the same for all of these. This is my anomeric carbon. It has an ether group going down here and an ether group going down here. So this is a full-on acetal. So then this is not reducing sugar. Move on to my next one. This is my anomeric carbon. I have an ether, and I have an alcohol group. So this is a hemiacetal. So I'm going to call this reducing. Then for this one, it's not cyclized, but I can cyclize it to make it more clear. So again, I'm going to just number it just for like practice. Only the things that are reacting in my reaction, I'm going to number. So my nucleophile comes in and attacks my electrophilic carbonyl carbon, pops this open so we can have alcohol, right? And so I do my Haworth projection. I'm not going to draw the whole thing. I'm just going to see if I made I'm just going to look at the anomeric carbon and its substituent. And so this is 6 and this is 1. So at number 1, when we attacked the carbonyl carbon, we created an oxyanion. This charge right here, an oxygen with a negative charge. And so it's in your body. It's going to grab onto a proton and make an alcohol. So at number 1, it doesn't matter if it's up or down. That's just dependent on the kind of carbohydrate that it is. I guess I'll just do it right. So this is a D. So whatever this is, an H2OH. Oh no, yeah. So it just matters on if it's alpha or beta. And so for this case, it'd be trans to each other. So this is my alpha anomer. But regardless of that, is the anomeric carbon a hemiacetal? Yes, because we have an ether and an alcohol group. Ether. Yeah. So then reducing sugar. These epimer ones are really easy. So epimers are just diastromers, and they're diastromers, like instead of having 2 stereogenic centers out of the 4 stereogenic centers change in configuration, only 1 can change. So we have a total of 1, 2, 3, 4 stereogenic centers. For it to be an epimer, only 1 of these can change. That's exactly what I'm asking you to do for each of these. It shifted. I'm sorry. Sorry about that. But to solve this, you number it as usual. Carbonyl carbon is 1, 2, 3, 4, 5, and I'll just number this as 6, like it's a yes. And so at carbon, we want an epimer and number 4, and we have an epimer, or we want an epimer, and number 3. There we go. So I'm gonna write everything as normal. CHO. I'm doing the 3 epimer first. This is carbon number 3, so this is going to be the stereogenic center one that flips. Cool. Everything else stays the same. That's my 3 epimer. Notice how only the 3rd carbon that I labeled flipped from the left to the right. So let me write my 4th epimer. Write everything as normal. And this one's the one that flips. So there we go. At carbon number 4, 1, 2, 3, 4, I have an epimer. That's my 4 epimer. And then again, I show you D-glucose to really drive it in you that you need to know this. Let's do these last ones. So these are predicting the products, and these aren't too bad. So let me just, I messed up on this one. Let me see. I believe this is just Ag2O. And so this is, it looks different, but it's the same as we've been working out usually, like what we've been doing. So it's like if we're doing an anhydride and we're reacting it with an alcohol, because all of these are my alcohols right here. So we're reacting it with this whole anhydride, and we just get a substitution reaction. So all of this will be my good leaving group. It leaves and this hops in. So I get an ester. So then that means for all of these alcohols right here, all of them, I get an ester. So let me start writing it. Adding a whole acyl group. Acyl is just like the functional group. Yes, where you have the carbon right here and the carbonyl right there. And then it doesn't matter what's over here. It's just this whole group is your acyl group. And how you abbreviate it is you just do AC. So instead of writing everything down out, I'm just going to put EC. Okay, so now I'm going to do the same thing. So this right here, same thing with this. I'm just going to substitute all these hydrogens for this whole R group, so 2 carbons. I guess I'll just draw that out. I'll do another example. So remember, this Ag2O provides an OH group. And so that OH group that you're reacting it with will turn this into a negatively charged oxygen. This is your nucleophile, and we have this as an electrophile. Leave the leaving group, and it's like a little Williamson ether synthesis. So now I'm going to erase that. And now start drawing. So I'm just going to add my 2 carbons to every alcohol. That's all. This one over here. So this one looks difficult, but it's what we've been doing this whole time. So I'll just show you step by step. For the first reaction, we have a good nucleophile, and we're doing an acid, so we're protonating this right here and making the carbonyl carbon more electrophilic. Easier for this cyano group to come in and attack, right? And that's exactly what it does. Right, everything else the same. Oops. Let me change this. Just so you can see. This carbonyl carbon is this carbon right here, but we attacked it with a cyano group, so it turns into an alcohol with a hydrogen in it, right? So then I just don't know where like my OH group is going to be, like on the left or on the right. So I'm drawing this wiggly line so we can draw both of the epimers at the end when we have to put our products. And so this CN that we added is up here, right? And I do my second reaction, which is a hydrogenation reaction. And we know that hydrogenation reactions like to get rid of a pi bond. So that's also exactly what I'm going to do. So carbon, it's hydrogenated. Nitrogen, hydrogenated. Let me see if, okay, yeah, that looks good. So for the final reaction, number 3 is H3O plus. And so I'm going to look back at my second reaction and notice how this group right here, there's a carbon double bonded to my nitrogen. And so what we usually have seen that in is imines. And we know that when we hydrolyze imines, use H3O plus, we separate it into a carbonyl and an amine group. And since it's an imine, we know that we're working with a primary amine or just an amine group. So an amine and a carbonyl is what I should get. And that's exactly what I'm going to be getting. Turn this all into proper carbons. And this is where I get my carbonyl. So this is going to be an aldehyde. Why isn't this right here? Cool. We get this epimer, and remember how we have it on the squiggly line because we don't know if it's on the left side or on the right side. So now I'm going to have to write both of the epimers. So in this one, it's on the right side, so I'm going to draw it over here on the left. And everything else stays the same. There you go. And those are your 2 epimers. And so notice how over here we have 1, 2, 3, 4 carbons, whereas over here I have 1, 2, 3, 4, 5 carbons. So since we're building it up, we're adding carbons to it. This is a synthesis. We're making something. So the name of this one is, I believe, it's wool degradation and Killian-Fisher synthesis. Killian-Fisher synthesis? I'm not even going to spell it. It's the synthesis. Killian. One of those. Okay. But for this next one, answer the following questions about this peptide. So peptides, it's the building blocks, or the peptide bonds are what makes up the proteins. And so what this question is asking is how many residues make up this peptide? And so in amino acids, what binds everything together is basically the peptide bonds. And so peptide bonds are these carbonyl bonds with this nitrogen right here. This bond right here, carbonyl between this nitrogen is the peptide bonds. And so this is going to help us, I guess, in B, not even in A. So label all the peptide bonds by drawing an arrow to them. I guess we can just do that one first. I was trying to do A, but I just described this one. So I'm going to label this right here because I have a carbonyl right here and a nitrogen. So I point at the bond. Carbonyl right here and a nitrogen. So I point at the bond. Carbonyl right here and a nitrogen. Point at the bond. So we got B. Label all the peptide bonds by drawing an arrow to them. So we have 3 peptide bonds. But that doesn't mean that we have 3 residues or amino acids to make up this peptide. How we can figure out how many amino acids make up this peptide is, okay, check it out. This is the basic structure of an amino acid. I'm not going to do the little things. So they're called alpha amino acids. We just say amino acids just because it's like a shorter term, but they're alpha amino acids. And so at the alpha carbon, which we just know is 1 carbon away from the carbonyl, the alpha carbon is right here. We have both hydrogen for a lot of the amino acids, an amine group, and the side chain, which over here I have, this is valine, so this is my side chain. It's a hydrophobic side chain right here. And the side chain is what usually changes for all amino acids. That's how you differentiate all of them. But the alpha part is going to tell us how many amino acids we have, because at every alpha we have a different side chain, and one amino acid has a side chain, right? So sure. So the thing that I'm going to do is I'm going to find all my alpha groups on my dipeptide bonds. So this is like my linear dipeptide bond. So on this line and only this line, I'm going to find my alpha, because everything else above that is my side chains. So I found my carbonyl, and the carbon next to it is going to be my alpha, so that's 1. Find my carbonyl, carbon next to it is going to be my alpha, so that's another 1. Find my carbonyl, carbon next to it, 1 carbon away is my alpha. And this is not an alpha because this is a side chain. So remember to follow this polypeptide chain right here of only the carbonyls and the nitrogens, and then locate your alpha carbons. Okay, fine. Okay, so this is another thing that I got confused on for the test. This like really messed me up. Instead of this, I want you to draw what it actually looks like, the C double O minus, which is just carbon double bonded to oxygen with a negatively charged oxygen. So this is another carbonyl, and we locate our alpha. So that's something that really messed me up on the test, because I just didn't remember like small thing like that. So then I count up all my alpha carbons and check out they have all their side chains. It's phenylalanine, cysteine. This is asparagine. And this is threonine. So that's 4 different amino acids. And so I'm going to put 4 of them, make it up. And you don't need to memorize the amino acids for this class. So then just do that little strategy. Check out all of your alpha carbons and then answer. That's it. For letter C, label N and C terminus. So this one's simple. The amine side is going to be your N terminus. That's makes sense because it's an amine group, so it has a nitrogen. And then your C terminus is going to be your carboxyl terminus, so it has carbon in it. So all you look for is your nitrogen on the side. So this is my N terminus. Terminus means like ending part. And this is my C terminus because it ends on carbon. This is my C terminus. And that's all. So this is a lot of your exam, so make sure that you pick up on these because they're not too bad. It's just the practice on all of this that you need for this test. Yeah, that was the end of part 2. And if you guys have any other questions about this test or any of the content that you needed covered for this test, you can just text me on GroupMe and I will try to make another video out of it so I can help everyone else too. But yeah, good job this semester. And you can always contact me for anything. Like I'm studying for the MCAT right now. If you ever need MCAT help, let me know. That'll be practice for me too. And you can always keep in contact with me if you need help in college. So yes, yeah, that's all. And I'll see you guys